We welcome the next speaker, Glenn Christian. Glenn was a lecturer at the University of Oxford, where he worked on low-latency beam-based feedback systems. Now he's a senior FPGA engineer in the accelerator control groups at the Diamond Light Source, the UK's national synchrotron. Today, he presents the PandABlocks framework for flexible runtime configuration of system on chip. Thank you.
Thanks, Filiberto. Am I on? Is the microphone on?
Try.
Is it on now? Yeah, okay. Great, yeah, thanks for giving me the opportunity to talk at the event today. So yeah, I work in the accelerator control group at Diamond. I'm going to talk about the PandABlocks framework for Zynq systems on chip. But before I start, I just want to give a brief introduction to what Diamond is for those who may not know. So, as Filiberto just said, Diamond is the UK national third-generation synchrotron light source based in Oxfordshire. It started operation in 2007. We currently have about 33 beam lines covering a vast range of science activities using light from infrared up to hard X-rays. So the machine is a 3 GeV, 500 meters circumference storage ring with a 100 MeV Linac booster synchrotron injection. And we're currently going into our upgrade phase, so we were recently awarded the finances for the upgrade. It's a £500 million upgrade to a fourth generation light source. This will start at the end of 2027, where we'll rip out most of the accelerators, replace them, and add some new beam lines. So there'll be a lot of work to do, and then we'll start up again, hopefully in 18 months following the start of the dark period. So in Diamond, we use FPGAs in quite a large range of activities throughout the facility, in the accelerator controls, in beam position monitors, power supply controllers, and detectors. But today I want to talk about about PandA, which is a beamline application. So the motivation here is what's called hardware-triggered scanning. So in my kind of naive way of explaining it, we have a sample on the beamline, and instead of just move and acquire data, we want to continually keep the sample in sort of continuous motion in all degrees of freedom and continuously trigger detectors. This obviously enables us to speed up scans quite a bit, reducing dead time, and several of the experiments, especially biological ones where there's fast dynamics going on, really require the scan to be done as quick as possible without exposing the sample, say, to too much radiation. But what we need to do then is we need some way of being able to marry together the positions of all the encoders in the system to give us the position of the sample with the images taken by the detector in order to reconstruct it. So to do this, in collaboration with the Soleil synchrotron 10 years ago, we started up some hardware called PandA, which stands for Position and Acquisition. And this is a flexible FPGA-based encoder platform, processing platform, which allows triggering aligned on either time or position. We now expanded the collaboration to include Max4, ALBA, and DESY, and together we're working on the design for the upgrade of PandA with PandABox, which is called PandABox 2. This is just a brief introduction to the hardware. So the original hardware was a 1U 19-inch rack. Based around the, so I'll see if I can get the laser to, oh no, okay, sorry everyone, I'll forget trying to use the laser. So it's based around the PicoZ SOM with a Zynq 7030 on board. Then we have at the top 4 encoder daughter cards, which are basically 4 RS485 line driver receivers, and which connect to D connectors on the back panel. And this allows us to run a variety of protocols: Quadrature, SSI, BIS, absolute encoder protocols. And these daughter cards are site customizable, so different facilities can put their own customized card for their own requirements. So on the front panel we have TTL and LVDS inputs and outputs for detector triggering. And we also have a Spartan 6. Basically, we were running out of pins on the original Zynq, so we put in a Spartan 6 to act as I/O expansion. Then SFPs on the front for communication, and also an LPC FMC socket. And we support a variety of different FMCs, for example, for ADC cards, or just additional digital I/O. So this is all available on open hardware, and the actual board is commercially available from Quantum Detectors, a company in the UK, a spin-out company. So as well as the kind of European collaborators who are the developers of the platform, it's also used in many other facilities around the world. For example, NSLS2 in the US, HEPS in China, and Sesame in the Middle East. So that was the hardware, but then I want to talk more about the framework, the software and firmware framework. So this is all available on our public GitHub. We have obviously the FPGA firmware itself, which I'll talk more about in coming slides. The root file system for the Zynq, for the PS part of the Zynq, which contains, of course, like the first stage bootloader, U-boot, kernel image, etc. And then also TCP server and kernel driver, which then allows us to communicate with the running device. So this gives us an interface to the configuration status registers in the firmware, and for streaming data via DMA. Then we also have a custom web UI, which is the most commonly used interface for the system, but also a Python client and Tango and Epic's support into the control systems. So this slide is just here basically to re-illustrate the dichotomy of PandABox being the hardware and PandABlocks being the kind of software and firmware stack. So when I talk about Panda, or maybe being ambiguous, but just want to make clear the difference between PandABox and PandABlocks. So I mentioned earlier that we have about, say, 33 beam lines, and this is used in many facilities around the world. So what we don't want to do is support multiple versions of firmware for different beamline experiments or different facilities. So we'd like to have a single firmware image, ideally, for the platform that everyone can use. But of course, all these different places and beamlines are doing completely different experiments. So we have the concept of functional blocks that can be kind of configured and rewired at runtime. And these are kind of multiplexed together with these various buses. I'll see if I can get the pointer to, here it is, a bit slow. But so we have functional blocks, which could be things like a lookup table, set reset gate, pulse generator, etc. Then we also have hardware blocks on the carrier, which are more specific to the actual hardware, things like TTL outputs, LVDS. And then, so running through the firmware, we have two sort of large buses. One 128 thing called the bit bus, which connects all the blocks together and can share bits on that bus. And then also a position bus, where we can share basically 32-bit words. So basically, to get this to work, what we're really doing is we're turning the FPGA into lots of multiplexers, basically. And we can kind of get away with that because we run at a fairly modest pedestrian clock speed of 125 megahertz. I think if we tried to run faster than that, we would really struggle. We'd struggle to make routing, place and route work. So this is just an example of the framework. So here we have, this is in the web GUI, so we have two input encoder blocks, which are their value, which is on this orange position bus, is going to a sequencer block. Then this sequencer block has a bit bus output that's going both to an LVDS output, in this case, probably to trigger a detector, but at the same time also triggering the position capture, so we can capture these encoder values in tandem with triggering the detector. So some time ago now, we invested into an auto-generation framework so we could basically auto-generate as much of the underlying code behind this as possible. So our goals were to firstly simplify the inclusion of any user-generated functional blocks, so make it easier for someone just to write their own block and bring it into the framework. Secondly, to be able to implement arbitrary combinations of soft and hardware blocks. And then third, to simplify the targeting this to other Zynq-based hardware platforms. So to do this, we have a set of ini files. So at the top is the app.ini, which the job of this is to specify the soft blocks that are in the design, but also it also specifies the hardware target. Then on the hardware side, we have a target ini file, which specifies the hardware-specific function blocks that the hardware can support. Then the block.inis themselves specify the register interface for the block and any other information such as additional IP that it's using or any additional constraints required. So all these ini files join together with Ginger templating to generate VHDL files and TCL files, which then are brought together with hard-coded VHDL for the carrier, specifying the carrier I/O and tickle for the carrier. And then also all the module VHDL here, which is the VHDL code supporting the individual blocks. So these all come together to form the FPGA configuration package. And this is all, this uses the Ginger 2 templating engine I'll show an example in a minute. But it's all makefile driven. I just wanted to mention as well the register interface. So we have the 128 kilobyte memory mapped registers supported. So we can have up to 16 instances of up to 32 design blocks. And in it for each block, 64 32-bit registers. In reality, we use almost a tiny fraction of that, like 1 to 2%, say. But this is a very simple interface. So it starts off as AXI light from the PS, and then it's translated down to a simple acknowledge and strobe, and there's just the VHDL signal defines the definitions for this. So it's very simple, just addresses data, strobe and acknowledge for both read and write. So I just wanted to kind of walk through an example of adding a new soft block. So in this case, I've actually just taken one of our simpler blocks, which is called clock block, which just gives basically a user-defined, divided down clock output. I won't go through the VHDL, but I just want to point out in the port list at the top, we have an enable signal, which will be coming from this bit bus. We have an output signal, which will be going onto the bit bus, and the periods vector, which will be provided by one of the registers. So I'll just zoom into this. So this is what would be our block.ini file. Again, very simple. And again, we just define the enable to be a multiplexer on the bit bus, the period to be a parameter, and the output to be a bit out going, as I say, onto that bus. We also need then a top-level app ini file that specifies that we're using that. So again, this is just tells it the target is PandABox, and here's listed clock number 2, so there'll be 2 clock blocks in this design. Then the boxes in red here are the Ginger template and basically what's provided. That doesn't need to be written by the person implementing the block. So this is an example of the Ginger. Some of it looks like pure VHDL, but some of it's kind of Pythonified templating. But that would then produce this clock wrapper here, which does the job of instantiating this clock block. And also, I haven't shown it, but also instantiates the register interface. Okay, I will move fast. Also instantiates the register interface. So I wanted to say a little bit about synchronization. I mentioned earlier we'd ideally have one VHDL code for all applications on one hardware platform. But unfortunately, that's not possible when we're trying to support multiple FMCs and different applications on SFPs. So we can't multiplex, unfortunately, multiplex the SFPs for different configurations of MGTs. So I wanted to just talk very quickly about some of the SFP-based blocks that we use for synchronization and data sharing. So we have, firstly, the PandA event receiver. So this is a port of the Micro Research Finland timing protocol that we use at Diamond. So this is a simple 2 byte, where the first byte, the distributed bus, is the same each time, and then an event code sent afterwards in the second byte. That runs at 2.5 gigabit per second. We also developed a lightweight protocol so the first one, the EVR, gives us synchronization to the accelerators. Then we also have PandASync, which is a lightweight protocol for data sharing between pandas. So here we have 8 bit bus signals and 4 POS bus signals that can be shared, and in a kind of repeating 6-cycle repeating pattern. So one of the requirements for this was we wanted less than 1 clock cycle jitter between our systems. For that, we ended up using Pixo, which I won't go into details of here. Probably many of you are familiar with the phase interpolator controlled crystal oscillator IP from Xilinx. But using that, we're able to achieve about 20 picosecond timing jitter between different TTL outputs on separate pandas. I'll skip the next point because I'm running really short. I'll skip. In fact, I'm really running out of time, aren't I?
Yes,
3 minutes. Okay. I will talk very briefly about the FPGA power brick. So this is an example of porting where we ported it to the Ultrascale. So this was developed in collaboration with Faraday Motion Control. So we basically have a power brick motion controller with an ST1 from Inclustra inside, a custom FMC, and then custom line driver cards that allows the ST1 then or the XU6 to be able to eavesdrop on the encoder signals going to the power brick. So basically, instead of having 2 separate boxes, we can combine it all in one. This is just an example of one of the sort of original motivation for porting to the Ultrascale. As I'm running short of time, I'll skip this next slide because there's quite a few steps here, and I'll just move on to PandABox 2, which is being developed now currently. So this is also a collaboration with ALBA and DESY and Max4. Again, it's a 1U platform, but the idea is that the actual base card only takes up half the width, so we can also have it as a double height, half width form factor. The front and rear panels will be interchangeable. So there's no longer that it has to be encoders on one side and digital I/O on the other. You could have digital I/O both sides, or indeed just come up with a customizable I/O panel if you didn't want to use encoders, for example. Then screens, 4 SFP sockets, and LPC FMC with 12 MGTs pinned out, and also clocking support for White Rabbit built in. So an area where we invested heavily in recent years was in the developer environment. First of all, creating a developer container for all the PandABox builds. There's Rocky 8, we include inside it the ARM cross-compiler, AMD kernel, DOICE tree, U-boot sources. One of the main advantages is a static Python environment. So one of the bugbears with lots of people developing is somebody would update their Python and then end up making changes to the build system, and you'd find your build doesn't work anymore. So now we avoid that. So we don't put the AMD tools in, though. We map these in externally. We also do CI on using GitHub Actions for all 3 of the main repos, the FPGA, rootfs, and server. Have unit tests, both for Python, which test the actual framework itself, and the Ginger templating, etc. And then HDL tests for all of the functional blocks. And CI, we do a CI build of the firmware images using a sort of self-hosted GitHub runner on our local cluster. And that becomes then the de facto source for our releases. Just a couple of other recent developments. We've been looking a bit at Yocto. So the current rootfs, which we've been using, is a build root-inspired system that's been used for many years. And that's small and maintainable by us, but not so easy for our external collaborators to get to grips with. So Yocto, we're hoping, is more industry standard and will remove the burden of maintaining packages ourselves, and hopefully avoid some of the headaches that we have every time we want to upgrade a Vivado version or a kernel version, etc., and find that we open up rabbit holes as to why things are not working. Another thing is CocoaTB. So we've recently moved our block block level HDA tests from the Vivado simulator to CocoaTB. This obviously makes life easier for Python developers to get involved in the verification, and really massively speeds up the time taken for the simulations as well, because we can now use GHDL and NVC, which we couldn't before, due to the fact that for some reason our test benches were in Verilog, so we had to rely on Vivado's mixed language support. So I think I will just move on to the summary there. So hopefully I've demonstrated that the PandABlocks is a flexible framework for supporting multiple beamline applications with, ideally, if we can, a single firmware image per hardware variant, modulo things like SFP applications, which have to be thought of as an extension of the hardware. So it's a reusable firmware software stack that can be targeted to any Zynq 7000 or Zynq Ultrascale Plus platform. I was also trying to allude to the fact that in some respects you could think of the hardware as reusable. The new PandA being more customizable in terms of its I/O is no longer necessarily just an encoder processing platform. And we're actually finding many uses for it now on the Diamond 2 storage ring, where especially for one-off systems, where we were thinking to go micro TCA, and now we're realizing actually we happen to be designing something that fits all the requirements. So we don't need to buy in some expensive micro TCA hardware for some of the one-off systems. And this is a growing collaboration, and we welcome new contributors to the framework. And talking about the collaboration, there's just a list of the current collaboration members, people working on either the hardware or the firmware aspects. And thanks for your attention.
Thank you very much. Let's see if from the audience, we have any questions. Yes, one in the middle.
Hello, Gordon Marinkovic, PSI. I was wondering, how do you load the firmware into the FPGAs? You have these Spartanas as well, the Zynq. So I wonder whether you're able to do that dynamically, or do you have to do that first by JTAG cable or something like that?
So we load up the rootfs first, which is boosted off of SD card. And then we have a script that loads the FPGA firmware onto the Zynq. And in principle, you could have multiple FPGA firmware sitting on the card and use I2C to inquire as to what configuration you've got and load the appropriate firmware. But we haven't quite done that yet. So another question.
May I do a follow-up question? So that means a firmware upgrade, you first load it, and then you reboot the whole box in order to load the FPGA firmware?
No, if we don't need to reboot in order to load the FPGA firmware. We just load a new bit stream in.
Okay.
Another question?
Hello. Yeah, thank you very much for your presentation, really interesting. I would like just to maybe recap to see if I understood correctly the idea of the framework. So you have the Python, is basically a Python-based framework, what is generating the VHDL. So I would like to understand what is the challenge or what is the idea behind it. Because, well, we already know that, this is a high-level synthesis way of seeing the things, that something that we previously saw that it was not.
Yeah, so we've kept things as low level as possible, really. But what we can't expect all of our users to be VHDL experts. So we're trying to make it as easy as possible for people just to bring in a particular functionality and not have to worry about plumbing that into the rest of the design. So they write their functional block, and they can simulate it, add it to the test suite, and then the idea is that the Ginger framework will take that block provided it's being used, and deal with the plumbing in and avoid people manually. Because the other problem is when you've got multiple people on large projects like that, if you start changing the plumbing, you make all sorts of problems for other people later on.
And can you tell us, then I guess you have a big. I don't know how big a library of modules that are integrated to this framework already.
It's not so big. It's only things that have really been needed on beamline experiments, really. There's probably about 20 or so functional blocks that are the soft blocks that you could just pull into any design, and then blocks that support hardware, for example, supporting MGTs or particular outputs, the encoders themselves or the trigger, the triggering.
Can you tell us what are the main challenges of this framework building this? Is dealing with the hardware or dealing with the software?
I don't know. I mean,
Okay, so my final question is, do you think that this type of framework has a possibility out for general purpose, for other applications?
well, I tend to use it I use it, say, for example, I was bringing up a board for a completely different project and I wanted multiple transceivers. And after messing around a little bit, I decided, I'll just port PandA to it because suddenly it brings everything up, and I've got access to I2C on all the devices, provided I've set that, I didn't really have to, I skipped the part where I showed kind of how to go through the porting to a new hardware platform, because that would have taken a few minutes. But yeah, I tend to use it, but then it's because I'm familiar with it. But then we'd hope that, that people may be inspired, at least if they wanted to do something similar without using the actual, our actual framework.
Okay, thank you.
Okay.
Can take another question from the middle.
So basically, you develop your own Python library to convert the VHD, all the RTL code and
well, we didn't know this. This is the part for the templating. That was called Ginger or Ginger 2, and we didn't develop that. We just make use of it.
Because there is like an open source project. I think it's called MyHDL, which does the same thing. Like
we did look at one point at MyHDL, but it didn't quite do what we wanted. We wanted to still maintain strict control in places by staying at the low-level VHDL, but just simplifying the plumbing aspects. We could have used maybe MyHDL for that, but it just didn't seem to. It wasn't the right fit at the time.
Thank you.
Okay.
Okay, in the interest of time, we thank Glenn again.